Okay, normal distribution, page 2. Packets of coconut milk are advertised to contain 250 milliliters. Akshar tests 75 packets. He finds that the contents are normally distributed with a mean volume of 255 and a standard deviation of 8. So the mean would be 255 and the standard deviation is 8. So that means plus 8 would be 263, plus 8 would be 271, plus 8 would be 279, minus 8 would be 247, minus 8 would be 239, minus 8 would be 231. Okay. All right, now next question. Sketch a normal distribution diagram to illustrate this information. Okay, we already did that. Even if they don't ask you to do this, it's very useful to do this. Find the probability that the packet contains less than 239. 239 is less than 239 would be these two parts, right? So remember, this is 34, this is 13.5, this is 2, and this is 0.5. So the purple area would be 2 plus 0.5, so it would be 2.5%. Okay. Find the expected number of packets that contain more than 247. Okay, so this is kind of a new kind of problem. Expected number. We haven't done that before. So the expected number of packets that contains more than 247. So the first thing we're going to do is we're going to figure out the percentage that contains more than 247. And you could add up all these numbers, but remember, half of the normal distribution diagram is already 50%. So you know it's 50% plus 34%. The total is 84%. Okay, so the answer for this is 84%, but they don't want to know the percentage. They want to know the expected number of packets. To find the expected number of packets, multiply the percentage times the total number of packets, which is 75. So if we multiply 84% times 75, 0.84 times 75 equals 63. So the expected number of packets to contain more than 247 would be 63. Okay. Now it looks like we're going to have to use the calculator. Okay, so just like we did in the investigation. Jordy delivers daily papers to a number of homes in a village. The time taken to deliver the papers follows a normal distribution with mean 80 minutes and standard deviation 7 minutes. Okay, so sketch a normal distribution diagram. So we're going to have 87, we're going to have 73, we're going to have 94, and 101, and we're going to subtract 7 here. It would be 66. Subtract 7 here, it's going to be 59. Okay. All right, sketch a normal distribution diagram. Okay. Find the probability that Jordy takes longer than 90 minutes to deliver the paper. So we're just going to draw the lines here. Okay. Probability that he takes longer than 90 minutes. Oh, look at that. There is no line at 90. That means calculator time. Okay? Let's see. Because the calculator can figure out any interval, not just the ones that are exactly on the standard deviation line. So this is going to be 90. So the way we do that is, well, the calculator just needs to be given the mean and the standard deviation. We do second distribution. We go to the normal CDF function. And then we give it, for the left interval, we're going to give it 90. And for the right, the lower interval, 90. Upper interval, infinity. So we're going to give it 1 double E. Where is double E? There it is. 99. And the mean is 80. That's in the middle. The standard deviation, one interval, is 7. Okay, and then we just paste. And it gives us 0.06 7656, and in percentages, that's actually 7.66%. Okay, and that would be 7.66%. Okay. Remember that to find the percentage from here, you would multiply it times 100. That's why we got 7.66%. Georgie delivers papers every day of the year, 365 days. Calculate the expected number of days on which it would take Georgie longer than 90 minutes to deliver the paper. We know 7.66% of the days he takes longer than 90 minutes. Now, if he delivers 365 days, what's the expected number of days? You would just multiply 7.66 times 365. 365 times 0.0766, and then we change it back into a decimal, right, to find the expected number. It's 28, okay? So if we do 0.0766 times 365 on the calculator, and that will give us 28 expected days that Georgie takes longer than 90 minutes to deliver the paper. Number 2. A set of 2,000 IQ scores is normally distributed with a mean of 100 and a standard deviation of 10. Calculate the probability that is represented by each of the following diagrams. Okay, so 100 is the mean, standard deviation of 10, and these are just like 3 different distributions. We can do this with the 68, 95, 99 distribution, I think. So like, for example, this one. 100 is the mean. 90 is the mean minus 1 standard deviation. So this section here is like 34, right? And then this part would be everything left. So it would be 50 minus 34. 50 minus 34 is 16%. Okay, so the first one is just 16%. The second one, let's see, it is also exactly on a standard deviation line. So remember, the first slice has 34, the second slice has 13.5, and the third slice has everything else. Let's see, 34 plus 13.5 is 47.5. The rest of it is 2.5, right? So there's a 2.5% chance that it's there, okay? And then for this one, again, conveniently in intervals of sigma. So here we have 34% of the people, here we have 34% of the people, and here we have 13.5. So we just add these up, get 68 plus 13.5, that is 81.5%, right? We did that addition before, which is why I remember it. Find the expected number of people with an IQ of more than 115. Now this is hard because we didn't figure out the percentage for this yet. So let's do that. So the mean is 100. The standard deviation is 10, right? And then they want from 115, which is right here, and they want to the right, right? Because this is more than 115. Okay, so let's use a calculator because 115 is not on a standard deviation interval. We can't just use the rule we've been using. So the lower limit would be 115 because it's on the left. The upper limit would be infinity. The mean would be 100, and the sigma would be 10. Paste. Okay, and so the percentage of people would be 6.68%. Oops, 6.68%, and I would multiply that times the total number of people to get the expected number of people with an IQ of more than 115. And there are 2,000 IQ scores total, so I'm multiplying times 2,000. So I would multiply 0.0668 times 2,000, and I'll do that with my calculator. And I get 133.6, okay? We could say 134 maybe on the answer on a test so that we show that we know that there is no such thing as 0.6 of a person.